Okay, so my work is purely experimental, and it's condensed matter physics, low temperatures, and two-dimensional semiconductors. So here are my collaborators, and as you can see, they came from all over the world. I'm in US, she's in US, Russia, US, Netherlands, US, Russia. Okay, so why two dimensions? It's the first question. We all live in three-dimensional world, right? It turns out that condensed matter physics is much more rich in two dimensions than in 1 and 3. Right? If you look at the list of Nobel Prize received in condensed matter recently, quantum Hall effect two-dimensional system 85, high TC superconductors 87, two-dimensional system, fractional quantum Hall effect 98, also two-dimensional system. The last one, graphene 2010. So indeed, it looks like three-dimensional systems, they have too many electrons. They're hard to control. One-dimensional systems are too simple. Two dimensions is a good boundary between those two. So here is my outline. I will just mention, I will not talk about scaling theory, I will just mention the conclusions. Then I will talk about our samples, about our experiments. Then it will be mostly public relations stuff. I want to show you how new things are accepted by society. Yeah, so first of all, what's localization? Before Anderson, people thought that distinction between metals and insulators is very simple. If you have your Fermi level in the conduction band, you have a metal. If it is between conduction and valence band, you have semiconductor or insulator, depending on how wide the band is. Anderson showed that it's not so. If you have too many scatterers in the system, scatterers means like random positive charges, then electrons will be, as you said, localized. So suppose we have a good piece of metal. It has several scatterers. So all metals have scatterers, right? So electron is coming, scatters once, second time, third time, but wave function is just a sine wave. So electron can penetrate infinitely far away. But if you have too many scatterers, like shown here, electrons become localized. Wave function is 0 at a certain distance, and it cannot extend by more than a certain localization length, as Anderson called it. And this example, in classical world, right, it's famous Einstein's relation. If a drunken person makes random steps in all possible directions, finally he will be far away, infinitely far away. Like number of steps, square root of the number of steps from the initial position. But in quantum world it's not so. And electrons are quantum particles. So they interfere with each other. Suppose we consider two-dimensional system here, right? So that's a plane. That's our two-dimensional plane. The drunken sailor also walks in two dimensions, right? Flat square, for example, right? So, due to quantum interference, electrons will always come back after some scattering into dimensions. No matter how few or how many scatterers you have, they will always be localized. And it was shown by RG analysis by this group, Abraham, Sanderson, Riccardello, and Matrishnin, who were later called the gang of four. A two-dimensional system is always localized and cannot conduct at 0 temperature, exactly 0 Kelvin. If you go away from 0 Kelvin, of course, it will conduct, but conductivity dies exponentially with decreasing temperature. And it was done in 1979, and practically immediately it became one of the most influential paradigms in condensed matter physics. But what they didn't do, they didn't consider interaction between electrons. And the electrons do interact, right? They're charged particles. So conclusion was excellent and everything is fine. It was, of course, immediately confirmed by experiments. Strictly speaking, of course, experiments are not done at zero temperature, right? They're done at finite temperatures. But you can know they predicted logarithmic temperature dependence. So you go down in temperature and conductivity goes down logarithmically with temperature. And that was observed in experiments. So it looked like the equation was settled. But electrons do interact, right? And they interact via Coulomb forces, as we heard from the previous speaker. And Coulomb forces is what? It's inverse distance between electrons, right? So you have, if you have n sub s electrons on a per square centimeter, then Coulomb interaction is just square root of number of electrons. Right? But Fermi energy, kinetic energy, is proportional in two dimensions to the number of electrons. So if you plot both Coulomb energy and Fermi energy, you can see that inevitably, at very low electron densities, the Coulomb energy will become stronger than Fermi energy. Potential energy is stronger than kinetic energy, and then you probably cannot just disregard the interactions between electrons. So suppose I want to characterize strength, relative strength of interactions by this dimensionless parameter, R sub s. It's simply a ratio between Coulomb energy and Fermi energy. So this ratio is proportional to inverse square root of electron density. The lower the density of electrons, density is just let's think of density is number of electrons per square centimeter. Right? It's a two-dimensional system, so it's square centimeters, not cubic centimeter. So if this ratio R sub s is less than 1, we have electron gas. They don't feel each other, they're just randomly running around. Now, suppose we have extremely strong interactions between electrons. So strong that the ratio is bigger than 35. Because the numerical calculations show us that if the ratio is bigger than 35, electrons are forming so-called Wigner crystal. They're trying to do their best to keep as far as possible from each other, right? To minimize the potential energy. So it will be either square lattice or triangular lattice or hexagonal lattice, but it will be lattice. And it will have a long range order. Once again, numerically it was shown that it should happen when interactions exceed Fermi energy by a factor of more than 55. But between those two parameters, it's a huge area. Nobody knows what's going to happen there. There is no analytical theory. There was no analytical theory. There was no even calculations. So the question must be solved experimentally. Now, our samples, I will just show a picture of a typical sample. It's what you have in cell phones, in laptops, field effect transistor. Simple thing, right? We have semiconductor, usually it's silicon, but not necessarily. And we have oxide, it's just an insulator, and then a piece of metal operated on top of oxide. So it's metal, oxide, semiconductor, field effect transistor. And you have contacts. Now, suppose you apply positive voltage to gate relative to silicon. And then electrons are attracted and they form a very narrow level, two-dimensional, not level, sorry, layer. Two-dimensional layer right here on the interface. It's not exactly two-dimensional. It has a width of about 3 nanometers, depending on the voltage you apply. But it's still, it can be considered as two-dimensional because it's less than the wave function of a electron. So they can move in x and y directions, but they cannot move in z directions. Now here is the top view of the sample. Electrons leave below this white track, that's our gate. So we apply current, pass current between source and drain, and measure voltage between two potential contacts. It's a standard. Then divide voltage by current, we get resistance. And want to see what's going to happen with resistivity at low temperature. So that's what it was, what that what it is expected to be according to the Gangle 4. I plot here log of resistance in units of HOV squared. It's about 25 kilo ohm. I'm not going to go into details why we measure in those units. It's quantum of resistance. And I plotted the function of temperature in kelvins. So as we approach from 0, those different curves correspond to different number of electrons. So here we have a lot of electrons, here we have very few electrons. But when the number of electrons goes down, disorder also increases because you don't screen so well. And you can see, we go down in temperature and resistance increases exactly as it's supposed to do according to the conventional theory. Here, you cannot see actually on those curves in a scale I show here. You cannot really see this increase. But if you look in the microscope very carefully, you will see that it does increase. Okay? So that's traditional poor quality sample. Now, what happens if you take a high quality sample? High quality means you have very few scatterings, very clean. So again, we have lowest electron density, has highest electron density, but actually highest and lowest, they're not so much different from each other. It's the difference by less than a factor of 2. And again, I plot log of resistance as a function of temperature. And if we have strong disorder, few electrons, we have a polarization, right? We go down in temperature, and the resistance grows by many orders of magnitude. That's what it's supposed to do. But if you exceed some critical electron density corresponding to this red line, you have an opposite effect. At first, nothing happens, or even maybe resistance grows a little, and then it goes down. And it's not a small effect, it's a factor of 10 effect. Okay? So it's completely unexpected, but it does look like a phase transition. It's a critical behavior. Moreover, that was sample actually, that's not our first publication on the subject, but that's probably better one. The first paper was published in 1994. That's a better picture. The samples are brought from Russia. And here is a sample made by Tim Klavik in Delft. That's a Russian sample, that's a Dutch sample. And if you put them one on top of each other, you see, the behavior is practically identical. The samples measured in different labs from different countries, they're from differently manufactured, but the behavior is very, very universal. Next, suppose we now apply parallel magnetic field, parallel to interface. So it doesn't induce any orbital motion, it only couples to electron spins. So here spins are random when electric field is close to 0, and then they become aligned. And you can see what happens to resistance. It grows, and then it saturates. So it looks like once spins are saturated, electric field has done all it could do. Nothing else can be done. It doesn't move. It doesn't change anymore. This, it was taken, the data were taken at very low temperature, 30 millikelvins, approximately 100 times lower temperature than it is in the open space. But electromagnetic field does more than that. It's not only increases the resistance, it also completely wipes out this critical behavior. You see? It looks like by applying magnetic field we came back to normal situation, to what we're supposed to see. When spins are aligned, the system behaves like an insulator. So it suggests some unusual spin properties. Somehow spins are behind this problem. Indeed, we measured the spin susceptibility. Here it's shown. G factor M is effective mass. But you can just think of this as a spin susceptibility. And as a function of electron density, it behaves like this. It goes like that. It follows this critical form, and it diverges at this point, exactly the point where we see the transition from insulator to metal. And as I promised, I will entertain you now. Reaction of referees. The data were obtained in 1993, the first set of data, and we sent it to physical review letters. That's the referee A. Everyone knows there is no zero temperature conductivity in 2D. Referee B. It's very interesting, but it's wrong. It's wrong. If it existed, it would be observed long time ago. And referee C. I cannot explain the reported behavior offhand. Therefore, it must be experimental error. Excellent. And then, of course, timeline. 93 discovered, rejected, proposal submitted to NS7 rejected, 94 rejected, 95 rejected, 96 rejected, and 97 rejected. Finally, at 97, something happened. A group from, Canadian group, Peter Coleridge, observed the same effect in a different system. And maybe people started to say, oh, maybe indeed something strange is happening in silicon. Then Israeli group, well, I call it Suez group, but in fact it was done by those two Israeli guys. Observed it in gallium arsenide. Here is a picture, it's very similar to what we see. And then it turned out suddenly that it exists everywhere. And once you take a clean sample, you can see this effect everywhere. So this paradigm, almost 35 years old, but at that time it was not 35, it was 25 years old, turned out to be completely incorrect. I mean, it's obviously correct for non-interacting electrons. But once you manage electrons to interact by reducing electron density, you can see this effect everywhere. And then it started. Physics Today, 97. Nature, 97. Once again, after discoveries of the quantum Hall effect and high temperature superconductivity, it is two-dimensional systems that provide a real surprise in condensed matter physics. And later, science, confide, hope, but still moving. Science news, long-standing question, the field answered. Real metals 2D or not 2D? Even an economist published a paper on our results. So what do theorists have to say? Turned out there are as many theories as there are theorists. First, scaling theory, non-Fermi liquid. Another non-Fermi liquid. Now, superconductivity, another type of superconductivity. And the third type of superconductivity is silicon. Silicon is not a superconductor, but if you believe, you can, of course, explain it as a superconductivity in silicon. Then, new quantum phases, unknown. Charge and discharging of traps, temperature-dependent screening, spin orbit scattering, whatever you can imagine. Finally, 2004, a real theory was constructed by those two Alexanders, Panus and Finkelstein. And they managed to publish their paper in Science, although Science doesn't normally publish theoretical papers. They show that there is indeed a quantum critical point separating metallic phase, which is stabilized by electron interactions, from the insulating phase where disorder prevails. And then did made some quantitative and qualitative predictions. Namely, they predicted what the phase diagram should look like. So, how much time do I have? How much time do I have? No, I have 25 altogether. So
you have a quarter, 15 minutes.
Oh, no, I don't need this. This is okay. I thought I was running off time already. So that's a phase diagram. It may look strange, these coordinates, but in fact you can consider x-axis as interactions. zero interactions is just no interactions, infinitely strong interactions. And vertical axis is a disorder resistance. So don't pay attention to the right top part of the phase diagram because it cannot be realized in the experiment. But you can see what happens here on the left side of this line. Right? At first, when interactions grow, resistance goes up and then it goes down and eventually should approach zero. But only if disorder is not too strong. If it is too strong, interactions first grow when temperature is going down and then start decreasing and the disorder goes to infinity. But between those two regimes there is a quantum critical point which probably corresponds to this flat curve on our data. Quantum critical point means that the temperature goes to zero and we end up at this point. Resistance, disorder, interactions, nothing changes once we end up at this point. And indeed, we see we change the temperature here by a factor of 30 or 40, and indeed nothing happens. Resistance just remains constant. So we were trying to reproduce this phase diagram, not reproduce, verify this phase diagram, whether it works or not. So we measured resistance as a function of temperature and also strength of interactions as a function of temperature. It's not really Coulomb interactions, it's spin-related interactions. And it turns out that both of them depend on temperature. So we have disorder and we have interactions, and we can reproduce, we can plot them on the phase diagram. Wait a second, I'm going to start here. So I just replot those data which I showed as disorder versus interaction. This is our experimental points. Those black lines are not experimental points, they're just guides to the eye. But you can see that basically we have the same behavior, right, as we have here on the theoretical phase diagram. At first, disorder grows when temperature goes down, and then it decreases. We don't see decrease to zero, of course, because our temperatures are finite. But also you can see that they form the same line, more or less like on this phase diagram. But if disorder is too strong, instead, it continues to grow when temperature goes down, so we follow this line. That's the qualitative phase diagram, but they also made a quantitative predictions. And yeah, I think I missed one slide, but theoretical slide. But and I show here resistance as a function of temperature and strength of interactions as a function of temperature. And they said, without any adjustable parameters in their theory, that once strength of interactions exceeds a certain value, I will not go into details what units these are, 0.45, certain units. The behavior of resistance should change from insulating-like to metallic. So here we have insulating-like behavior, here we have metallic-like behavior. And you can see it happens practically exactly 1.4 instead of 0.45. It's a theory without adjustable parameters, and it works absolutely perfectly. And here finally we can compare the shape of the curves with the theoretical predictions. Our experimental points are those dots, and black line is the universal curve. I've never seen such a coincidence between theory and experiment. That's a little worse. That's strength of interactions versus some reduced temperature. Black line is what they predicted. Experimental points, those dots, crosses, experimental points for different electron densities. But again, pretty good coincidence. So, summary. What happens in two dimensions when you have strong correlations, strong interactions? First of all, we can have a metallic state which was considered impossible for 25, now it's 30 plus years. And this metallic state is stabilized by interactions between electrons. And modern RG theory gives quantitatively correct description of the metallic state without any fitting parameter. Thank you.
Now, questions, please.
Yes, it's a hypothetical question, but would it help understand the issue better if you thought of resistance as a velocity? So, as a velocity. So, what you say is if a piece of material has a zero resistance, any speed, the electron can travel at any speed. If the resistance is infinite, there is no speed the electron can travel at in order to pass over the material. So what you have there is a boundary where at certain levels of you have the velocity suddenly dips away. It cannot go faster, if it goes slower, the velocity can go higher.
Yes,
the actual electrons can move faster or slower, depending whether they're above or below the boundary.
How to measure speed? Resistance easy to measure, right? Yeah, not so easy at those temperatures, but it's still speed. I just don't know.
What is the physical origin of extreme point, saddle point on the phase diagrams?
Sorry?
What is the physical origin?
Of the fixed point.
Saddle, critical saddle point.
I don't know what.
Type of
You mean this
point
one, right?
is saddle.
This one, right?
Yeah.
Yes. I don't know. You're on the border between between the machines, right? So, I cannot explain the theory at all. There is no qualitative explanation of the relation. Why electron and electron interaction stabilize metallic state? I don't know. I asked 100 times to those guys. Not only them, of course. They're the main people, but there are other people who do similar theory later and before. They didn't go so far as those. I asked all of them 100 times. Can you explain it somehow physically? Not just tell me, I calculated. just tell me what it is. No way. Properties of scaling. That's it.
Please.
Practically, how do you measure the strength of the interaction?
Yeah, that's not a strength of Coulomb interaction, that's spin-related interactions. So it's measured when you apply parallel magnetic field, which starts to align speeds. We know the strength of magnetic resistance is proportional to the square of magnetic field and to the strength of interactions. Yes. And coefficient, we can extract.
Other question? This is very important for me personally, because I have such two-dimensional arrays of electrons as families of quantum dots in a gallium arsenide crystal. And I think that this is a theory for small temperatures.
Yes, yes.
Only for small temperatures. Then if I have
It's
no
not really
temperature,
small.
I cannot have correlations.
It starts with the it starts with high temperature.
Zero.
No, zero is the strength of interaction. So it's so that's the direction of the temperature. You're down in temperature. So you start from room temperature and then, no, not from room, of course, because at room temperature you also have phonos, right? So you need to start where phonos are not important anymore, maybe 10 Kelvin.
Yes. And the distance between two successive electrons, which would be to have such
It depends on how
it's
many
a
you
spin,
have.
a spin interaction.
Yes, yes. So it's
10 nanometers, 10 nanometers.
10, 20, depends on how many you have. So 10 or
I
20.
have 10 to 0.16 on a meter, on a square meter.
So I can tell you it's inverse square root, right? So,
Yes.
and pi also.
Yes,
About
and
pi, so
in
you
this
have
case
10
there is a
minus
distance between
8,
them.
100.
No, 10 nanometers.
But then, I'm thinking atoms, yes. Yes.
Then at an optimal temperature cannot exist any correlation.
Below 1 Kelvin.
Thank you, Mr. Kravchenko.
Thank you.
Let's